this video I'm going to go over how to calculate energy of a reaction in another way. So there you can calculate it with bond energy, but you can also calculate it with enthalpy of formation. So enthalpy is almost the same thing as heat. So if you see Q or H, they're basically referring to the same thing. Enthalpy is basically the heat content of a substance or a system. So it's something that it's the energy of something specific, basically. So enthalpy of a reaction can be looked at instead of bond energy by the reactants and the products. So if I look at this reaction right here, I'm burning methane and oxygen gas while I'm producing CO2 and H2O. I can see from this diagram that CO2 and H2O have less enthalpy. What I can do to calculate the enthalpy of the entire reaction is take the enthalpy of making CO2 and water and then subtracting it from the enthalpy of formation for methane and oxygen gas. And that can tell me how much energy is released in this particular reaction. So the normal conditions that you have would be the gases are going to be at 1 atmosphere. Solutions will be 1 mole per liter, and the temperature is normally 298 Kelvin. So if any of these conditions change, you're actually going to change the enthalpy of formation, because people went and they measured the enthalpy of formation for lots and lots of different compounds, but in order to do that they had to set certain conditions, and these are some of the conditions. Now the enthalpy of formation, so it looks like this and it has a little f, is the enthalpy change when 1 mole of something is formed from its elements in their standard states. So if I'm looking at this reaction right here where I make ethanol, when 1 mole of this substance is formed, I'm going to use carbon, which is 1 element, and its standard state, hydrogen and its standard state, and oxygen and its standard state will make up this product. So when I say standard state, metals, most elements are just going to be 1 atom. So aluminum would just be Al, iron would just be Fe. But if you have a diatomic, diatomics will be found in their pairs like they normally are in most chemical reactions. So bromine would be Br2, hydrogen would be H2, iodine would be I2, and so on. Now if we have carbon, which you're going to see a lot in these reactions, it's just graphite. Now the important thing to remember is that if you have something in its standard state, the enthalpy formation would be 0. So we're going to write out some enthalpy of formation equations. So we're going to be making 1 mole of the product from its elements. So if I'm looking at this, the first one, CH3Br, I'm going to make this thing from its elements. Well, it's made of carbon, hydrogen, and bromine, and it has to be in their standard states. So carbon, when it's in its standard state, would just be graphite. Now, hydrogen also makes up this compound. When it's in its standard state, it will be H2. And then bromine also makes up this compound, so that's going to be Br2 because it's diatomic. All right, the next part would be to balance the equation. So let's do hydrogen first. Let me put a 3 here, 2 here, and that means that I need a 2 here. And I'm balanced at that point, but there's an issue with this. Anytime I have enthalpy of formation, I need to have just 1 mole of the product. So I'm going to reduce everything down so I have just 1 mole of my product. So in order to get this to 1, I can divide by 2. So I have to divide everything by 2. So 2 divided by 2 is 1. Again, it's going to be 1 for the carbon. All right. Now 3 divided by 2 here would give me 3/2, and that's okay. I can leave it as a fraction. And 1 divided by 2 would give me 1/2, and that's okay. It can be a fraction here. So this would be the correct enthalpy of formation equation for the first one. All right, let's look at another one. Okay, so this one is CH3CO C2H5. Well, this is made with carbon, hydrogen, and oxygen. So carbon in its standard state would be graphite. Hydrogen would be H2. And oxygen would be O2. Well, we got to balance it. So let's fix the oxygen first. I'm going to put a 2 here to make the oxygen balanced. But let's figure out how many carbons I have now. I have 1, 2, 3, 4. So 4 altogether, and then I've got 2 there, so that would be 8. So I have to put an 8 there. And then for hydrogen, I've got 3 plus 5, so that's 8 times 2. So I need to have an 8 here. And I'm balanced now, but I need to get this down to 1 mole. So I'm going to divide everything by 2. So CH3CO C2H5, 2 divided by 2 just be 1. 8 divided by 2 should be 4. Same thing for the hydrogen. 8 divided by 2 would be 4. Oh, not 8 here, just 2. And then 1 divided by 2 would be 1/2. All right, so now I've got 1 mole. Everything's in its standard state, and I'm balanced. Let's do one more. Let's do sodium nitrate. Okay, so for sodium nitrate, I am making up this product with sodium, nitrogen, and oxygen. Well, sodium, it's just a metal, so it's just going to be Na as its solid form. Nitrogen's a Brinkelhoff, so N2. And oxygen is also a Brinkelhoff. All right, so let's fix the oxygens. All right, that's going to give me 6 oxygens. It also fixes the nitrogen, so I just need a 2 here, but I cannot leave it like this since I've got 2 moles here. So I need the product to just be 1 mole. So 2 divided by 2 will give me 1. Divide everything by 2 then, so 2 divided by 2 would give me 1 here. 1 divided by 2 would give me 1/2. And 3 divided by 2 would give me 3/2. All right, so sometimes you're going to be asked to calculate the enthalpy of a reaction, and you might need to actually write out these equations. So just remember, it needs to be 1 mole of product from each of its elements in their standard state. All right, so let's look at an example where we're actually going to calculate something. So if we are given enthalpy of formations for the products and the reactants, it's very simple. We're just going to get the sum of all the products, the sum of all the reactants, and then subtract the 2. So in bond energy, when you calculate the energy with the bond energy, you do bonds broken minus bonds formed. Here you're kind of doing the opposite, okay? But this equation will be given to you on the AP test. All right, so let's look at an equation or an example where we will do this. Okay, so we have thermite. Thermite being burned produces aluminum oxide and iron. Or this is the thermite reaction with this and this. So we want to calculate the enthalpy change of this entire reaction given the standard enthalpies of formation for this and for this are -800 and -1600 kilojoules per mole. All right, so if we do this, let's write out the equation again. We have iron oxide, or iron 3 oxide rather, plus aluminum produces aluminum oxide and iron, 2 irons. All right, so we were given enthalpies of formation for the iron oxide, which was -823, and the aluminum oxide, which is this. Okay, so when we do actually have enough information to calculate the enthalpy of the reaction here, because the thing is, aluminum is in its standard state here, so is iron. So that means that the enthalpy of formation here is just 0, and it's 0 here. So we have all of our reactants and all of our products. So what we're going to do is we're going to multiply the enthalpy of formation by the coefficient, get the sum for each side, and then subtract. So we've got 1 mole here. Here I've got 2 moles, although it doesn't really matter because it's 0. Same thing here. And then here I've got 1 mole. So let's take the formation of the products, and that's going to be 0 plus negative 1675. And then we're going to subtract the reactants. So 1 times that would just be this, plus 0, and then you just simply solve. And then after this, you will get negative 852, and that's going to be kilojoules per mole. So basically, if we have this reaction happen perfectly in its with the perfect stoichiometry, we're going to release 852 kilojoules in this reaction.